Today we're going to be going over different ways of splitting n objects into k groups. So the first way we can do it is with distinct or distinguishable k groups, meaning that they're different and you can tell them apart with identical n objects. So our first example is with n cookies among k kids. So the kids will be different, but if you have cookies in a package, they are identical, you can't really tell them apart. So if empty groups are allowed, the way to find how many different ways you're able to split up these cookies with empty groups is going to be n plus k minus 1, choose k minus 1. So if we made an example, and let's say we had 7 cookies, and we want to split it up into 3 kids. Well, how we're going to use this formula is our n is our amount of objects, which is the amount of cookies, which means it's going to be 7 plus our number of groups, which is 3, minus 1, choose 3 minus 1, which will give us 9, choose 2. However, if we want no empty groups, with still the same rules of having distinct groups and identical objects, then we have to use the formula of n minus 1 and k minus 1. So what this means is, since we have no empty, if we had our 7 cookies and we had our 3 kids, and these were our 3 kids up top, we automatically place one of the cookies into each of the kids' groups, which leaves us with only the 4 cookies remaining, which is what we'll have to use the choosing formula for, and that's what causes it to be a little bit different. So this one will just become 6, choose 2. Because it's 7 minus 1, which is 6, and 3 minus 1, which is 2. Next up, we have indistinguishable groups and identical objects. So what indistinguishable groups means, if you split up a team into 2 groups with player 1, 2, and then on the other team we had players 3 and 4, this would be equal to 2, 1, and this would be equal to 3, 4, and 1, 2. So it means that permuting them or switching them around does not change the groups. The only way that it would change the groups is depending on actually who is on the group. So the first way we can do this is we could use the product of sums formula, but we want to try to find our coefficient. So the way to find the coefficient would be putting it into this large formula of n minus k plus k minus 1. And this is going to be choose k minus 1. And this is going to be x to the power of n. So for example, if we have n is equal to 5, so we have 5 objects, and we have our k as 3 for 3 groups, what we can do is change this formula to 5 minus 3, which is 2, plus 3 minus 1, which is 2, choose 3 minus 1, which is 2, which gives us our final formula of 4, choose 2. Now, for empty groups being allowed, this will change the formula, because instead what will happen is we will change it to n plus k minus 1, choose only k minus 1. So the only difference here is that instead we're not subtracting the k from the top of the choose function, because if you think about it, in our non-empty groups, and we had our 3, we need to place one of these objects into each of the groups to start so that there's not an empty group, which is what causes the minus k. But we don't need to subtract k here because we don't need to do that first step, as empty groups are completely fine. So with the same numbers as before, as n equals 5 and k is 3, this will become 5 plus k minus 1, which is 5 plus 2, which is 7. And that's going to be k minus 1, so it's going to be 7 choose 2. And since we're going to have our exponent, since we need our x to the n for both of them, this one will become x to the 5 because it's our n, and our x to the 5 here. And same thing for our empty groups. We're going to have x to the 5, which is what you would get if you expanded the product of sums. So for example, for our empty groups allowed, if you expanded the product of sums in front of our exponent of x to the 5, we would get 21x to the 5 if it was fully expanded. Now we have distinct groups with distinct objects where the order of the groups, the order of the objects within the group matters. So an example of this would be n books into k shelves. So if we had 3 shelves and we had 5 books, and we labeled them as 1, 2, 3, 4, 5, since they all have to be different. If on the first shelf we had 1, 2, and then the second shelf is 3, 4, and 5, this would be a different selection than 2, 1, 4, 3, and 5. Because the way that the order of the books is laid out is different, so in this example it matters. So the way this formula works is if we're allowing empty shelves, we're going to have the permutations of n and n plus k minus 1. So for an example of 3 shelves and 5 books, this will change into the permutations of 5 plus 3 minus 1 permuting 5, which will give us 7 permuting 5. And then if we're saying no empty, which I'll just label as n dot e so I don't write it out, this will just change to n minus 1 choose k minus 1 multiplied by n factorial. So what we'll have to do here is with our n, we're just going to same thing, 5 minus 1, which is 4, and k minus 1, which gives us 2. But because the order matters, which is different than our first example, because if you notice that n minus 1 and k minus 1 is the same thing as a distinct group with identical objects, the only difference now is because they're distinguishable objects, we have to permute all the different ways that they can be ordered along with the ways that they can be ordered in the group. That's why we multiply it by n factorial, which gives us the final 5 factorial. Now we have the interchangeable groups with distinct objects whose order within each group matters. So this is just going to be an add-on to the last interchangeable groups that we did, because the only difference here is that instead of having all the objects be the same, these objects will be able to be told apart. So the first thing we're going to do is non-empty, which follows kind of the same formula as our distinct groups with distinct objects, However, instead we're going to multiply it by the permutations of n permute n minus k. So an example of a question like this would be to rearrange n distinct letters into k words. So let's say we had n letters, and our n letters is going to be equal to 5, and then our k words is going to be equal to 3. So by words, what I mean is just a jumble of letters. So if we had A, B, C, D, and E, this will be considered as 3 words. So the amount of ways to make this happen with non-empty groups, meaning we can't have any word open, is going to be 5 minus 1, which is 4. Choose k minus 1, which is 2, multiplied by permuting 5 by 5 and 3, which gives us 2. And now we're going to change it to empty groups allowed. So the difference with this formula is it's going to be more of a sum function. Because as you see here, it says use the previous formula with k minus 1, k minus 2, all the way to 1, and then add. So what this means is if we have our same example as before, what happens is we're going to change it so that it would be n minus 1, choose k minus 1, multiplied by the permutations of n and n minus k, which is replacing the formula with k. Now, whenever you see a k, we're going to replace it with k minus 1. So it's going to be n minus 1, choose k minus 1 minus 1, multiplied by the permutations of n minus k minus 1. And then you'll keep going up until it's equal to 1. So to make this a little bit easier of an example, what we're going to do is we're going to have our n is equal to 3 and our k is equal to 2. So the way this would be done is n minus 1, which gives us 3 minus 1, which is 2, and then k minus 1, which gives us 1. And we're going to permute it, or multiply it, with the permutation of n, which is 3, and then n minus k, which gives us 1. Now what we're going to do is we're going to add it with our n minus 1 again, which is still 2, but now we're going to do k minus 1. 2 minus 1, which gives us 1. And we're going to subtract 1. And now we're going to multiply it with the permuting of n and 3 minus 2 minus 1, which this will give us the permutations of 3, choose, or 3 pick 2. And if you notice, since our k value here is now equal to 1, this is our last step. And if you put this all into a calculator, you'll get 12 different ways that we could have empty groups for this restriction. Now we have distinct groups with distinct objects where the order is irrelevant. So the example for this one is giving n books to k friends. So the way this works is if we have books, again, 1, 2, 3, 4, and 5, and I gave books 1 and 2 to friend 1, this would be the same as giving friend 1, 2, and 1, because they're still getting the same 2 books. It doesn't matter the order of which I give them the books. So when we're trying to find the amount of ways while empty is allowed, it's the easiest way we've had so far because it's just k to the power of n, which is just 5 to the power of 3 for our case. And if you have ever done probability with dice, you'll see that it's the same way as the total amount of possibilities to roll a die, because it would be 6 to the power of the amount of trials you have. It's the same formula for this. However, for empty not allowed, so non-empty, we have a much more difficult formula. We have the sum as goes from 1 to k minus 1 of -1 to the power of I times k choose I times k minus I to the power of n. So the way this one would work is we need to have the sum of just following the formula. So if we use the same example, or if we use a new example of k is equal to 2 and n is equal to 3, this will get us from -1 to the power of 0, because that's our I, and then k, which is our 2, choose I, which is 0, multiplied by k minus I, which is 2 minus 0, all to the power of 3. And now we add -1 to the power of 1, plus, or -1 to the power of 1, multiplied by 2, choose 1, because that's our new I, and then it's going to be 2 minus 1 to the power of 3. And since we have to go up until our value of I is k minus 1, and if you notice, our new value of I here is 1, which is the same thing as our k minus 1, because that's 2 minus 1. So this will give us a final answer of 6 if you put it into your calculator. Now our final way is interchangeable groups and distinct objects, and the order does not matter. So it would be dividing people into groups or teams, because just like the books in the shelves question, or the books giving to the friends question from before, it doesn't matter who's on the team, because they're still going to be the same team. If person 1 and person 2 are one team, if you select person 2 then 1, it's still going to be the same team. So if we have our n is equal to 3 and our k is equal to 2, we're going to take this formula and try to plug it in. So we're going to have 1 over 2 factorial multiplied by the sum as I goes to 0 to k minus 1. So we're going to write it out. We're going to have a large bracket here. We're going to have -1 to the power of I, which is going to be 0. Choose 0, multiplied by 2 minus 0, all to the power of 3. And then we're going to add, and you can split in the 1 over k factorial. It doesn't change it. So we could have 1 over k factorial again, or we could have it just at the beginning. To make it a little bit more simple, I'll just have it at the beginning. And it's going to be added by, we're going to have -1 to the power of 1, choose 2, or multiplied by 2, choose 1, multiplied by 2 minus 1 to the power of 3. And again, just like we had before, we're going to go up to k minus 1. And since our I is equal to 1, which is the same as k minus 1, this is where we would stop. Now, to have empty being allowed, the difference here is we're going to use the same formula of 1 over k factorial multiplied by the sum of x minus 1, I equals 1, of -1I, k choose I, multiplied by k minus I to the power of n, but we're going to take the sum, this sum, and then we're going to add our k, k minus 1, and k minus 2. So, for example, if we're going to have our 1 over k factorial, which if we use the same as n being 3 and k is equaling to 2, well, 1 over 2 factorial, and then we're going to have it multiplied by -1 to the power of I, multiplied by 2 choose 0, 0, multiplied by 2 minus 0 to the power of 3, plus -1 to -1 to the power of 1, multiplied by 2 choose 1, multiplied by 2 minus 1 to the power of 3. And that's where that will get stopped. But now we have to add it again, because now we need k minus 1 all the way up until it's equal to 1. So this will be -1 to the power of 0 multiplied by, instead of k, it's going to be k minus 1, which is going to be, so if I write out the formula again, it'll be 1 over k minus 1 factorial multiplied by the sum as I goes from 0 to k minus 1 of -1 to the I multiplied by k minus 1 choose I multiplied by k minus 1 to the power of n. So this will then become -1 to the I times k minus 1, which gives us 1, and this will be 0, and then k minus 1, which gives us 1 minus 1 to the power of 3, which will all go to 0, but we're still going to multiply it by 1 over 1 factorial. So this will be our new formula for if empty groups are allowed for this restriction.